Okay, there we go. All right. So let's move on to new material. Most of the product of some homeworks that you've done, you will simplify the same way, just using that redundancy rule. It works out really well. And oh, shoot, I shouldn't have erased it. What I was trying to point out is when you start writing out those terms and you start getting A or, because you'll see AA, and you go, oh, well, that's just A. And then you go A, B, oh, don't need to write it. A, C, don't need to write it. A, right? You don't even need to write those terms because you can see how obvious they simplify. Okay, that was the point I wanted to make. The last point I wanted to make with that. Let's introduce a new term, and we'll pull this back to the K-maps that we discussed last time. Start with an easy K-map. Something like this, and we'll label it this way. So you'll see them, okay, there's this new idea of don't cares. Now what a don't care means is I don't care if it's a 1 or a 0. I don't care if it's a min or a max term. Now we'll get into a real example of where this comes up, but the general rule is it comes from having invalid, let me make sure I do this right. Invalid, impossible, or irrelevant inputs. So it can't happen, it shouldn't happen, or if it does, we don't really care what does happen. Those are the three kind of situations where don't cares. In the K-map, you're going to see something like this, a D. That's don't care. I've seen some textbooks do it as X, totally fine. So again, what this says is I don't care what that value is. I can treat it as a 1 or a 0, meaning I don't have to include it in order to complete cover. I can cover the K-map without including that D or X, the don't care. However, if it is convenient to use, I can. So you'll notice, group of 4, in this K-map, it is convenient to use that don't care. And so my expression from this arises from, well, let's look at what doesn't change. Well, since it spans the entire length of the top row, the only thing that doesn't change is C, it's a 0, so it's C bar. And then it's or AB, right? So I get to use that don't care as a benefit, as added simplification. Let's look at a different example, same kind of thing. All right, is this too small? Or is it okay? Okay. Yeah. Let's say this K-map. Now, I must circle the 1s to complete cover, but I don't need to worry about this D, so I can leave it out, I don't care. And therefore, F is just simply equal to C bar and, well, it would be A bar. Right? So I can leave this don't care and say it's a 0, because I don't care. It's not important to me. So you're going to see that. I'll start using it in some more complicated examples as I start building them up. But I want you to have a concrete idea of why don't cares exist and why they're important, because they aren't some mathematical arbitrary thing that we use just for esoteric reasons. They come up all of the time in real design. Now, a good and easy one. Think of, I mean, you guys are all mostly young, but old school alarm clocks use what we call a 7-segment display. And you'll see this some other places, right, that has 7 LEDs. And it lights up different LEDs to show different numbers. So for example, if I want to show 7, so here's LED, let me use a different color so it's clear. LED 0, 1, 2, 3, 4, 5, 6. 7 segments. If I want to display the number 7, then I just light up 0, 2, and 5, right? Because then I get, kind of looks like a 7. Make sense? Everyone follow? All right. So now, what we could say from this truth table is that, well, before I get to the table, there are 7 different LEDs. And there are 10 different numbers that I can display. Each LED then is represented by 4 bits. Because 10 is more than 3 bits can handle and less than 4 bits can handle. So we're going to end up with extra bits that just lines in that truth table that don't have an assignment. Well, let's add an extra one. We'll add an E. So we'll have 0 to 9 and E. So in case you need to say that there's an error, there's a problem, we'll throw up an E. Okay? So let's do that truth table. And I'm going to do LED 0. Okay? Okay, that's a big truth table. All right. This is why we like this, the expression, right? F is equal to the sum of min terms, yada, 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 right? Because it's a lot easier to write that expression than it is to write this truth table. And okay, so when does this LED light up? Is the question. When do I want it on? When should this light be true? That's what the design question is. Well, we can just walk through the numbers, right? Is it on when 0? Yes, right? Because we're going to go around the outside. Is it on when 1? Oh, wait, sorry. Is on when 0, so I get a 1. It's not on when I have 1, and I can label these if it helps you. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now here I'm at, I'm at row 10, 12, 14, and 15. But what we also know is that for 10, we can't display 10 on this. There's just no hope. So that is a trivial or irrelevant input. If that happens, something went wrong. So 10 is don't care. And again, I don't care if you use X's or D's. And that's going to be true for 10, 11, 12, 13, 14. And then I said I wanted to reserve 15 for E. Right? E is going to light up LED 0. So it's true. Just take a moment, fill in the remaining truth table for numbers 1 to 9, and then I'll go give you guys just a second to do that, and then I'll fill it in to make sure you guys are following the idea. Okay, I'll just go through this. It looks like 2 is lit up, 3 is lit up, 4 is not, 5 is, 6 is, 7 is, 8 is, 9 is. I think. Anyone disagree with any of those? Okay, now we can hopefully, and you will right now, take this truth table using that map and put it into the K-map. Okay, so what I want to point out for this K-map, because we're starting to get familiar with going truth table to map, is that if I were to give you the expression of this, right, it is F is equal to the sum of min terms, 0, 2, 3, 5, 6, 7, 8, 9, and 15. Right? If I gave you this expression, you don't have to write out the truth table. You don't have to take that time. You could if it helps it be clear. But if you have something like a K-map drawn out and have it clearly labeled that these min terms are 1, 2, 3, 4, and so on, you can just draw out the K-map and drop the ones in directly without going to the truth table, right? So I'll continue on. So what I did is I just did the first 4, 1, 0, 1, 1. Oh, before I move on, I'm pointing out that this is the order if I do A, B, C, D. And if I instead do the other way of drawing, I wrote it where I did A, B, C, D, it's this route, right? It's horizontal. So just keep it straight in your head which way your min terms count up, depend on which bit you place where in the K-map. That's an easy one to screw up, so just be careful of that one. As is, because I have the K-map, I don't have to worry about the exact min terms, so I'm just going to follow through 4 at a time. Oh, third and fourth column should be flipped. Good catch. Oops, I just forgot what that one was. So it is 1, 1, XX. Okay, we good there? All right. So now, if we weren't using don't cares and we're like, oh, it's supposed to be off in these other ones, we would have a whole bunch of zeros. But as it is, this is really just a massive block of ones, right? So take just a moment to draw in, using the don't cares, your implicants. starting with the biggest ones that you can find, remembering that they're grouped in 2 to the n ones as either rectangles or squares. So 2, 4, 8 are valid. 6 is not. Okay, so as I said, I like to look for the biggest blocks of ones I can find. This is really convenient, right? So here I have 8. We like 8. Right, nice big. Here I have 8. Now I have 2 ones left that I've got to take care of, right? Now, a mistake that I've kind of seen people making is that they would just take this one and 1, 1 and do a 2, right? But again, overlap is good. It's completely fine as long as it's necessary to cover. So let's just do a square. I can't do 6, that's not allowed, but I can do the 4 in the center. And then this one, I don't see any, what do you see? How do I group this one well?
The corners.
The corners. Okay, that's your K-map. Go ahead and turn that into an equation for me. I'll start throwing the equation.
Just want one term, or do you want all of it?
Go for it, the whole thing.
Got C plus A plus B and D, and then plus not B and not D.
Does anyone disagree with any of these terms?
That's what I got exactly.
Perfect, great, good job. Okay, so there's our function for one LED. What do we do if we want to make the next LED? The same thing, we just make a new column next to this guy. We would call it LED 1. And then we would set about filling in the truth table for 1, right? And then you'd end up building 1 circuit for each LED, and then you'd be done. Hopefully now, if I throw a 7-segment display question on the exam, you will have a good clue of where to start. All right, well, let's use this as a nice opportunity to move on to the next idea. So we've got K-map, we've got don't care, we're at 4 variable K-maps. What happens if I want to use a final circuit that is a product of sums? Well, let's build a product of sums expression for F using the same K-map. And I'll use a different color of marker for the product of sums, or the max term implicants. So what I want to do is I want to circle the zeros instead of the ones. But just like the case of the ones, X's count as don't cares. They can be zeros. Okay, so I have a 0, and he has nobody adjacent to him that is don't care or another 0. So he stands all on his own, right? This 0, however, has the benefit of an adjacent don't care. That is a valid implicant. I can't make it bigger, unfortunately, because I've got a 1 blocking the square here, and I've got a 1 blocking the square here. It's kind of blocked in by itself other than that. And now, very similarly, I'm going to write the expression for the sum of product. And I'm going to walk right where you're standing. Okay, same idea. We look for what doesn't change. Unfortunately, nothing changes here. So we write this as not A, not B, not C, D. But they're not ANDed together. This is a product of sum. They're ORed together. So not A, not B, not C, or D. And product of sums were ANDed together. This one, which the terms that don't change are B and C and D. So, and then the ones that are knotted are B is fine, C and D are both knots. The other term, right, I've used it before, complement. I take the knot as the complement of D. Okay, but there's one thing that's not quite right here, because what I'm not interested in is the min terms. I'm looking for the max terms. So I actually go and I add a bar to every single one of these terms, because I'm looking for the complement of this. So I find what hasn't changed, and I take the complement of those variables. And we know if we take the complement twice, if we go not, it cancels out. And that, hopefully, is our product of sums expression for F. That's all. That's the only difference between sum of product and products of sums. Is sum of products is you find the implicants by circling the ones, you find the variables that don't change across that implicant, and then you write them down in a sum of products expression. For product of sums, you find the implicants using the zeros. You then find what doesn't change and write the complements of those variables as a product of sums expression. Make sense to everyone? Okay, good. So the last thing that I need to show is this is not quite the full expression. So for the min terms, I'm saying f is the min of all of these. Well, let's say f is the, I used this one once before, sum of the max terms. And my max terms, this is nice and easy to write, really, right? Because it's just 1, 4. But I also need to keep in mind, where are these don't cares? You'll notice that there's no expression part that shows me where these don't cares are. So what we do is or d of, well, where all the don't cares are. 10, 11, 12, 13, 14.
Would you do that on the min terms as well?
Yes, and it wouldn't change. You would still just write d of those.
Does that always go with the maxes or?
No, so I could append this same thing to this expression as well. And that's how I would express don't cares somewhere. Okay, so something that I would like to point out to you guys is sometimes, like in the 2.14 example that I did earlier in class, right, is the homework, you guys did this homework. If you're given, say, a product of some expressions and you're not sure what that minimum expression should be, you can turn that expression into a K-map and then see what that minimum expression would be. Sometimes because of the selective implicance, right? You might have multiple potential answers, but you can at least see what the potential answers are. So keep aware of that as a tool. Min-terms are a way of finding out the answer and then doing all of the algebra. Now, also be very aware. So our exam is open notes, open book, open internet, so long as you don't post your own content. I'm going to say when we get to the exam, don't use, the question will probably say, don't use an online digital logic calculator, simplifier. This is important because if I say that, you can't do it. And it's trivially easy for me to write an expression that they can't solve the way you would solve it. Because I understand their algorithm, so I can make these a trap question to see if you're doing it. Just letting you know. So if it says, don't use an online calculator, show all your own work, be very careful of using the online calculator because it's very obvious when you use it in certain ones. So make sure you're getting the practice is what I'm saying. Don't just rely on the crutch of the online calculators. It's okay to use it to make sure you're right. I'm all on board with that. Just make sure you're competent for the exam. Okay, I can use a simpler, I'm going to erase all of this and do one more product of sums K-map just so you all feel comfortable with those examples. So let's say that I want to write up the expression f is the sum of mins 0, 1, 4. And then I want you to find for me the minimum, simplest possible product of sums expression of that. So you'll notice that I've given it to you in the form of min terms, and product of sums means I want the max terms. This doesn't stop you from doing it because it's just as easy to write this K-map.
Is there 3 variables?
3 variable K-map. Yeah. So you can tell how many variables you need by the maximum number that you see here. So if I see a single number over 7, right, I have to go to a 4 variable K-map. Because 2 to the 3 is 8, and then we count from 0 to 7. So again, I know as long as I define it this way, my minterms do 1, 2, they're counting up top to bottom and then horizontally. So 0 has a 1, 1 has a 1, and 4 has a 1. So 0, 1, 2, 3, 4. Okay, go ahead, find your max term implicants, and then turn that into an expression. That what we got? Great. So now I wanted to do this nice simple 3-term one because what I want to show you now is if you end up in a situation where you have only a product of sum expression and say it's really complicated to simplify and you need it to get to sum of products. There is actually a really easy way that we can do this. And we do it by capitalizing on the fact that inverters in modern digital technologies are nearly free. And when I say that, it's kind of confusing. What it really means is most digital logic circuits end up generating both the original variable and its complement at the same time, regardless of what you program. So it's just there to be accessed. Even if it's not, making it as 2 transistors, it's tiny. So inverters are not really a big concern as far as cost goes. It's a low cost thing to do. So if I need to turn this into a sum of products, I can just say, let's solve for F bar. So what is F bar? Well, the complement of F is just not that whole expression. What theorem would we use to simplify this? De Morgan's. So step 1 is we turn the and into an or, and we complement the terms. So complementing B, and then I complement not A or not C. Right? Don't skip a layer. And now I just use De Morgan's again on this term. Bring down the B, say A, C. Now, if I design that circuit, you'll see that I end up with this guy, where here is F bar. If I just add an inverter at the output, That's it. Right? Anyways, that's a quick, easy way to jump between the two forms, is just find F bar. Okay, now we're going to move on to the next fun topic in K-maps so that we can get the homework assignment out that I want to, which is what happens when you have 5 variables. Now, there's actually 3 ways that I know to do this, and there's, I think, a couple more in the book. One of the ways that I don't teach, that one of the other professors will sometimes if he teaches this class, is called variable entered maps, or map entered variables, so either VEMs or MEVs. Now what these do, I'm not getting into. It's a way that you can handle essentially any number of variables using a K-map. It's not really necessary, because if you find yourself using more than, say, 6 variables, you're not going to be doing it by hand. I just can't imagine you do more than 6 variables by hand ever. And if you did use one of the algorithm processes that they have in the book, which we're not going to cover, so don't worry about it. I just want you to be aware that other method exists. What we do is one of 2 ways of drawing 5 variable K-maps. So the first way is simply by extending the K-map. And this is still A, B, C, D, but this one is for E bar, and this one is for E. So we're 0s here, 1s there. Another way that you could see this written would be to just shift everything a little bit. Let me erase here. Erase the E. And what you would write it out is ABC, DE. ABC, DE. The way we handle this is make sure I do this right. Okay, sorry, I'll get out of the way for a second. So what I'm doing is I'm still counting in gray code, but I have 3 bits of it. And I need to make sure that I don't change more than 1 variable as I cross from here to here. And somehow I think I messed this one up. Let me double check if I can pull this off though, because we need to end up back at essentially something like 1, 0, 0, right? So that makes this 1, 1, 1. And say that again. 1, 0, 1. Okay. So this way has its disadvantages. The advantage being that, let's fill in a K-map here for it. Okay. Something like this, where we can see that because of the logic adjacency of the horizontal row, that these ones and those ones are adjacent. So I can wrap all the way around and snag that for here. Now, what we don't necessarily sometimes see is that it is possible for some of these in the middle to actually be adjacent to some of these over here. But if you draw it this way, it's fine. And you would just solve this like so, or you'd say this is adjacent to those, this one here. And then you just make sure kind of visually that this one isn't actually adjacent to something over there. Because 0, 1, 1 is adjacent to 1, 1, 1, potentially, right? So if I had a 1 here, then I actually would have that. Those two blue ones are a minterm. They're logically adjacent because they differ by only 1 bit, A. That's hard to see here. The other way to do this. Let's extend them. Sorry, I didn't drop 4 on these the first time. I forgot the horizontal lines, but same idea. Okay. We'll just write it like I did the very first time where I say A, B, C, D, and then label them E bar and E, so we keep track of them. And then we don't worry about logic adjacency across the way. What we do instead is we say they're both their own K-map. But we picture them as one over the top of the other. They're stacked. So we have to visualize that. Now, I kind of liked, when I first started, I liked the first way because I'm actually really bad at 3D visualizations for whatever reason. I took the Air Force officer qualification exam one time, and they show these pictures that are like airplanes in different orientations and a picture of a compass and a gyroscope, and you have to tell which way is up and which way is north, essentially. And I was terrible at that. I can't picture in 3D very well. I've gotten okay in the realm of K-maps. Okay, so I'm going to stick to one of the examples, so if I butcher this, I don't get too far off track. Okay. So now we need to find what is logically adjacent in it. Well, we can say the obvious ones, right? These 4 are logically adjacent. But it also extends up the level or down, however you want to picture it, to these 4. So I actually have 8 in a cube. So these are stacked, those ones are over. They are not mirrored. So the last one was kind of mirrored, right? Which made the stacked difficult to see, difficult to visualize. This one is easier to visualize the stacking, but occasionally harder to see the adjacency between, well, 1, 0 and 1, 0 here. Because in the mirrored one, those ones would just be next to each other, the other style. Okay, so now, same thing goes. These 2 can go up a layer to the other E. They share, I apologize, I'm going to add an orange circle to this so that I have a different color to reference. And then I'll use the black one for the last one. So we have one remaining one that we need to cover, right? To complete the cover, I need that one. And there's no fancy tricks for this, so we'll just borrow the one right below it and call it good. So now go ahead and see if you can write the expressions for this. Right, this is a sum of product using min terms. It has 3 implicants, blue, orange, black. Go ahead and write them out.
I have a question.
Yes.
These are like, this is a group of 4, right?
Yes, they're a group of 4.
This is a horizontal 4.
Yes. Well, it says vertical 4. So if you picture then we have something like a 1 here and a 1 here and a 1 here and a 1 here. So I am circling the orange on this plane. And that's more of a visualization of these two, but
Yeah.
it's easier to draw in the corner than elsewhere.
Same question on the previous one. It's basically just like holding that and whatever is in those matches.
Yes, yes, yeah. So in the previous one, we're just taking this and flopping it over so that we can see.
Those are what are adjacent. And this is just showing what's adjacent.
Yes, exactly. So another way of saying it is the first method where I folded it down into a single plane makes it easier to see when you have logic adjacency at the edges at the cost of making it more difficult to see logic adjacency in the center of them. This one equalizes how difficult they are so that it's kind of a medium difficulty to see the logic adjacency for all of them. Okay, so let's go ahead and start puzzling this out. We can start by figuring out what doesn't change on each plane individually because it's the same, and then we'll worry about the up and down or not, right? So here, A doesn't change, B does, C doesn't change, and then because we go up a level, E does change. And then A is a 0, so A gets a bar. Okay. Now, everyone got that one, I hope. Does anyone want to take a stab at this, the orange one, the orange implicate? What?
Try. Wait,
Go.
so E wouldn't change there, right?
It does, because we're going orange to orange. That's why I tried to highlight this.
So it does.
Is these two and those two are logically adjacent, so we have a circle of 4.
Okay. Sorry, I'm just trying to think of the E right now, because I think I have that right, but, so E would change here?
Correct.
Okay, so is it A, not C, and D? That's what I have.
Is it? People agree?
Cool.
Cool. That sounds right to me then. A, not C, D. Yep. Answer sheet agrees with you, so that's a good sign. Jason, does Jason want to give a stab at the final implicant, the black implicant?
I think it would be A, not B, and not C. C.
Not C?
Yeah, not C.
What about E? What's the case for E?
I think it's opposite E. So I I'm a little bit confused with that part.
Yes, yeah, that's why I want to ask, to make sure you're doing okay, everyone. So in this plane, we're on E bar. On this plane, we're at E. That's why I've labeled them above. If I don't have implicant on both planes, then that means E doesn't change and is part of that term, that product term. So in this case, we should have E.
Okay.
So A is correct. B, oh wait, sorry, here, we're doing this one. So A, not B, not C, D does change, E doesn't. I believe that's right. Everyone agree? Go ahead and just write me the implicant. Not worrying about any other ones. If you had this blue one and this blue one, go ahead and write out just that implicant. You want to give a stab at it?
Not A, B, not C, not D.
Okay, so at first glance, this feels good because there's no E. We're going between the layers, so E does change. We're in the not A, B, not C, not D. Good job. All right, let's make this more complicated. What happens when we expand to 6 variables? Don't laugh. Berkeley made me do this with 7, so now you have to extend to hypercubes, and that's not fun. Again, if I'm putting this on an exam, I will do my best to remember to provide you guys with a K-map so that you don't have to spend that time writing it out. My exams, as a warning, I do keep mentioning them because I don't want you guys to be like surprised ever. They tend to be a little bit of a time crunch. So the better you know with the material, the better off you'll be. And if you know like tricks to make it go quicker. Okay, so now what we kind of have here is a 2 variable K-map where inside each of the, right, so a 2 variable K-map is just this. And we're going to call them E and F. But inside that 2 variable K-map are little K-maps. That's kind of what's happening. So we have E bar, E, but then on the side of it, we also have to go this direction. We have, shoot, I hate using F. We'll call it G. G bar and G. So now what's happened is it is a cube. So we can wrap around all the way from not G, not E, down to this one, right? So those two are logically adjacent. Then not G, not E is adjacent to not EG, but it is not, this one is not adjacent to here. So if you want to, we could label them a little more explicitly. So this map is EG. This one is not EG. This one is E, not G. And this is E, not G. Or not E, not G. Okay, so remembering that they are logically adjacent planes.
So on this one, would you need to worry about like multiple levels, or are we visualizing this as just one like flat?
Multiple levels. It's a
Okay.
cube. It's a 4x4 cube.
Okay.
Okay, and I'll use an example that I think does a pretty good job of highlighting this. Okay. Actually, I want to add onto this guy. We'll do another example, hopefully. Okay. So what we can start to see is, remember how I said not E, not G is not adjacent to EG. So that's problematic, potentially. So what we may want to look for is something like, I don't like this example as much, but these two are logically adjacent to those two. And then we're about out of time, and I'm not going to assign any 6 variables yet, so don't panic. We'll come back to this. If I had this map, so slight change to it, these 4, those 4, these 4, those 4, I'll just circle them to make this easier. So the orange implicant is a vertical column of 16, 4, 4, 4, 4, that extends the whole way through that column. Right? So that's the kind of thing we're going to start looking for in the 6 variable K-maps. Don't worry, I'll come back to this. I'm not yet sure if I'll do this to you on an exam or not. I'm not going to promise that I won't, but it's kind of fun once you get into them. So that's really all the time we have for class today. So if you have any questions, I'll hang out for a little bit, and then I'll have office hours just right down the hall right after class. Anyways, thanks, guys.
Will that cube in the middle you just did be BD?
Say that again?
Will that be BD?
Yeah, so E and G both change. And then you have the fact that B doesn't change and D doesn't change. So yes, BD.
So if you only connect bottom 2, you would put an E knot. If you were gonna, okay.
Yeah, so if E naught didn't change across the planes, so if I did this one and that one,
And you did the other 2.
which they are logically adjacent, then G changes, but E doesn't. So then it would be and not E. Yeah. It's not anything new, it's not anything that tricky, it's just getting the K-map down and trying to train yourself to see those layers.
So when you're setting these up in space, kind of how we're doing it in sign languages, this one becomes here. What's the next layer, what's the next layer, what's the last layer? Because this one can't connect to this one because it's that 3rd layer, correct?
So what you're looking at is if I'm going down one at a time, there's a couple different ways to visualize it, so I'm gonna have to think through this one. Is E not G is 0, 0. Then I have 0, 1,
So that's my second.
second one. Then 1, sorry, this one's 0, 1. So it's 0, 0, 0, 1, 1, 0, 1, 1. So it goes this one, that one, this one, that one.
So 1, 2, 3, 4. Okay.
Yeah.
Oh, good. Thanks. Okay, that makes sense. Because
Yeah,
when we're setting it up in layers to show that
Yeah.
this touches this one, it can wrap around to the back on this one, but this third layer, it doesn't touch anywhere, which is why it's not adjacent.
Yeah, correct. This one and this one is not adjacent, correct, yeah.
But this one, these two are because it touches and touches.
Yeah, so the real way to kind of visualize this is, it's almost like a donut of both planes.
Yeah.
So I kind of have one plane here, one plane that's kind of up here, one plane that's kind of over here, and one plane that's hanging out. Sorry, I'm not a world-class artist. So you can kind of just go around and you have 1, 2, 3, 4.
So 1, 4, and 2, but not 3.
Yeah, and so then my implicants are doing stuff like this.
Okay. Sure.
Or in the case of the big one, it's doing
Okay.
that.
And the reason why this one is included is because it's logically adjacent to these ones.
Correct. Yeah, I can cascade through logic adjacency.
Okay. But individually, these two planes are not connected. So if
Correct.
these two didn't have these 4, this would not be an adjacent.
Yes, yeah, so 3 or 4 needs to build me a road to, sorry, 2 or 4 needs to build me a road to 3.
Okay. Perfect. That makes way more sense.
So I actually had some questions on the homework last night.
Yeah.
I didn't turn in just because I was doing it and I wanted to talk about the CMOS stuff.
Yeah,
I'm doing like,
meet me in my office so I can get out for these other guys.
yeah, sounds good.